In the last lesson, we used the definitions or the identities, the reciprocal, Pythagorean, and quotient identities in order to find what the function values were for various trigonometric values. Today, what we're going to look at is how we can look at a diagram by drawing the angle within either the first, second, third, or fourth quadrants and use a corresponding triangle to be able to find out what the actual values are going to be. Here we see three different diagrams, one per quadrant, starting in quadrant 2, 3, and 4. And if we wanted to calculate, let's say we wanted to find sine of theta, okay? Theta would be the angle that's always starting at the positive x-axis and looping all the way around. But keep in mind that sine of theta represents an opposite side over a hypotenuse, and you can't have a right triangle with an angle that's bigger than 90 degrees. Likewise, if you were to look at the same situation here, and I wanted to find maybe sine of 210 degrees, there's not even a triangle with 210 degrees in it. But it doesn't mean that we can't find the actual function values. Instead, what we're going to be doing is referencing the angle that's left by seeing how far that angle is away from the x-axis. That's what we refer to as a reference angle. So the extra angle that attaches to the x-axis is referred to as the reference angle. So obviously 180 degrees is half a rotation, considering 0 degrees is on the positive x-axis. So if we wanted to figure out what that theta prime was, which is considered our reference angle, then theta prime, if the angle is in the second quadrant, is found by just taking that angle away from 180 degrees. So you take 180 degrees, subtract this angle, and all that's left is theta prime. Now, if you're in the third quadrant, you should notice that if this is the angle attaching to the x-axis, and this is 180 degrees, theta prime is a little bit more than 180 degrees. So if I wanted to compute theta prime in this circumstance, then notice that I would have to figure that if this is theta, I would take away 180 degrees, which takes away all of this. And all that's left is our reference angle. So our theta prime, if we're in the third quadrant, or our reference angle, is simply going to be the angle minus 180 degrees. So we don't want to memorize these necessarily. We want to visualize. We want to draw the picture every time and recognize that the reference angle is just the angle that's drawn to the x-axis. And if we're in the fourth quadrant, notice that this angle right here is the reference angle. This angle is almost a full rotation, which would have been all the way around at 360 degrees. So if I want to find theta prime in this circumstance, if we're in the fourth quadrant, we just simply have to start with 360 degrees, take away all of this angle, and all that's left is our theta prime. So this is how we're going to be using the diagrams, using the pictures here by drawing an angle in a particular quadrant in order to calculate what reference angle we're going to use. Now the reference angle, noticed, is always going to be an acute angle, an angle between 0 and 90. And we've already learned how to find trigonometric function values using acute angles. So now we're just going to take that a step further and find out how we can find trigonometric function values of non-acute angles. Look at this first example. We want to find a reference angle for 218 degrees. Now 218 degrees is obviously larger than 90, so it's not an acute angle. And so anything that's in the first quadrant would be considered an acute angle. Right? Well, by looking at this particular angle here, looking at this angle, any angle that's in the first quadrant is always going to be an acute angle. Now, if I were to look at the angle between the x-axis and that angle, this would not only be theta, but it would also be theta prime. It would also be its own reference angle. So now we've just got to think, well, if this is 90 degrees, and this is 180 degrees over on the far left side, by the time we get around to here, it's 270 degrees. We should be able to recognize that this angle here is going to be somewhere in between 180 and 270. So it's somewhere down here. And so we want to determine how far beyond 180 do we need to go in order to find that reference angle, okay? So if this reference angle is right here, then we're trying to find what is this, if this angle right here is 218 degrees, what our goal is to find the reference angle attached to the x-axis. So we just simply need to take, in order to find theta prime, we just simply need to take 218 degrees and subtract off 180. And when we do so, we find out that theta prime is 38 degrees. So that means that our reference angle in this case is 38 degrees, and we can now use that angle to find sine, cosine, tangent, and so on. Now, one thing that some people try to do is they always is try to find the reference angle by saying how far it is from the y-axis. That is not allowed, okay? So in order to find the reference angle, we're actually rotating all the way around. We're rotating around and finding out how far away we are from the x-axis. And we're going to see why that's the case shortly. So let's try 1,387 degrees, or 1,387. This one is far beyond 360 degrees. So before ever determining a reference angle, the first thing we want to find is a coterminal angle, okay? So in order to find a coterminal angle, remember we just have to keep subtracting 360 degrees until we're somewhere between 0 and 360. So let's take 1,387. And if we subtract 360 degrees once, well, that's subtracting 360. That's still going to be bigger than 360. If I subtract it twice, notice that I'm subtracting 720, which is still not going to be enough. If I subtract 363 times, then I'm subtracting 1,080. It looks like that's it. It looks like we're going to be able to subtract 363 times. So 1,387 degrees minus 1,080 degrees gives me an angle of 307 degrees. So 307 degrees now is simply the angle that we're going to use in order to find the reference angle. So we can take a look at another diagram here. 1,387 degrees is going to be one full rotation around, which takes me to 360. One more full rotation around, which takes me to 720. One more full rotation around, which takes me to 1,080. And now I've got to continue to go an extra 307 degrees in order to get to the correct location. So this is where we're now going to recognize that 307 degrees is no longer going to be in the second quadrant. It's now going to be past 270 and on its way to 360. So we need to figure out what is the reference angle here. So to continue, notice that the angle 1,387 is going to be still around from 1,080 until it finally gets to here. That's theta, that's 1,387 degrees. Our reference angle is going to be the angle formed connecting to the x-axis. So there's theta prime. So in order to find theta prime, we just simply need to see how far is 307 degrees away from a full rotation of 360 degrees. So we subtract, we get 53 degrees, and therefore theta prime is 53 degrees. So our goal here is to always find out what is the acute angle between 0 and 90 degrees that we're going to be able to use to find the trigonometric function values. Well, I'd like to revisit the diagrams of the two very special triangles that are going to pop themselves into this class over and over and over again. And so let's just recap that. If we had a 45-degree angle inside of a right angle, then that means that the complementary angle is also going to be 45 degrees. So now, if we were to set each of these two legs as 1, because I know that they're going to be the same size since they have opposite angles that are the same, the Pythagorean theorem gave us √2 as our hypotenuse. And then we derived from an equilateral triangle half of that equilateral triangle, which is now a 30, 60, 90 triangle. We could see that if the short side is 1, then the hypotenuse is twice as long. And the other leg opposite the 60-degree angle is √3. So if we just remember this special triangle, we don't have to derive it every time in order to find these side lengths, but we are going to be using these special triangles and computing the 6 trig functions of this particular angle. So let's say we're looking at 210 degrees. First of all, it's past 90, it's past 180, and it's not quite to 270. So I could see that 210 degrees is probably somewhere over here, okay? So what we want to do is be able to find if this is 210 degrees, we want to find the reference angle so that we're going to be able to draw a triangle. Because it's only with triangles that we could actually, or right triangles more specifically, that we could actually find what the trigonometric function values are. So this angle right here is our theta prime, and that's the angle we're trying to find. So let's try to find theta prime by recognizing that it's how far past 180. So we take 210, subtract 180 degrees. What we're left with is a 30-degree angle. So our reference angle is now 30 degrees. So the beauty of this is that now we could pick anywhere along this angle, anywhere we choose. And if we now draw another side of a triangle straight to the x-axis, then what we've done here is we've created a reference triangle. And this reference triangle is actually going to be used in order to find the trigonometric function values. We've just got to realize now that this is a 30, 60, 90 triangle. This triangle right here is just like this triangle here. It's just laying down on its side. So if we now have a 30-degree angle, we know that the opposite side must have a side length of 1. And we know that the hypotenuse must have a side length of 2. And it must be that the adjacent side has a side length of the square root of 3. And that should fit exactly into this special triangle. All we're doing is drawing the special triangle in the third quadrant. But we've got a slight little issue here that we've got to pay attention to. Since we're in the third quadrant, the x-coordinate is actually negative. And we should see that the y-coordinate is also negative. So notice that now that we have those values, we can find all 6 of our trigonometric function values. So if we want sine theta, I know that sine of theta, which is actually sine of 210 degrees, is actually going to be the same value as the sine using this triangle. So since sine represents the opposite side over the hypotenuse, or the y value over the x value, I know that the y value is -1. The x, or the hypotenuse, or the r value is 2. And therefore sine of 210 degrees is -1/2. And this refers back to what we learned with our identities, referring to what function values are positive in what quadrant. If we remember ASTC, we should remember that tangent is the only positive in the third quadrant. That means sine and cosine are both going to be negative. So keep in mind, we have two different ways to calculate all of these. We could either remember what the ratios are in terms of cosine of theta being x over r, or we could remember that it's the adjacent side divided by the hypotenuse. Either way we choose to do it, it's going to give the same result, because notice in this diagram, the x coordinate is -√3, the hypotenuse is 2. Or if we look next to this angle, the adjacent side is -√3, the hypotenuse is 2. Either way we choose to look at it, it's the same idea. And therefore cosine of 210 degrees is -√3 over 2. Tangent of 210 degrees is opposite over adjacent. So that's going to give me -1 over -√3. Now remember that we're not quite done until we end up rationalizing the denominator. The negatives cancel. So I just have to multiply by √3 over √3. And this gives me the ratio negative or positive √3 over 3. And now if I want to find cosecant, secant, and cotangent, I really could just take the reciprocals of each of those values. Or if I choose to, I could go back and do the ratio for cosecant. I know it's r over y, which would be 2 over -1, which obviously is going to give me a value of -2. But notice that -2 is just the reciprocal of sine of 210 degrees. So we're just going to do that. That's why I typically will find sine, cosine, and tangent. And once I find those, we'll just take the reciprocals to find the rest. So I see that 2 over -√3 is the reciprocal, but we've got to multiply by √3 over √3 in order to cancel the radical. And so the simplified version of secant of 210 degrees is -2√3 over 3. Finally, cotangent of 210 degrees is just the reciprocal. Now keep in mind, we have an option of either taking the reciprocal of this form, which would put the radical into the denominator, or take the reciprocal of this form, which would automatically put the radical in the numerator. So that's the one I'm going to do. I'm going to take the reciprocal of the first one, which is -√3 over -1, which means that this is √3. So the special triangles are really helpful to be able to find the trigonometric function values of some of the most common and important angles within the full rotation, namely 30, 45, 60 degrees, and any of those reference angles in any of the other quadrants. Let's take a look at an example of finding a trigonometric function value of some angle that's beyond the first rotation from 0 to 360 degrees. We can see in this case that we're asked to find cosine of -225 degrees. So we first have to figure out where is that angle? What quadrant is the angle in, and what is the reference angle? So we start off by realizing that if I were to have a negative angle, that going down and around is what makes my negative angle. So this is -90 degrees, so it's past that. This is -180 degrees, so it's past that as well. This is -270 degrees, so it's not quite that far. So that means that when we're trying to find the angle of 225 degrees, we just need to rotate this angle down past -90, past -180, almost to 270, but not quite. It's somewhere over here. And so it looks like this right here is approximately 225 degrees. Okay. So when I say -225 degrees, what I mean is this angle from the positive x-axis. This whole angle is -225 degrees. But if I'm going to find cosine of -225, I need to find my reference angle. So I need to find out how far is that angle away from -180. So there's a couple of ways to do this, but the idea here is that if I'm in the second quadrant, okay, then I'm going to take 225, and I'm turning them into positive angles just because that's the measure of the angle. It's just the negative showed me that I'm going backwards. And I'm going to take away the 180 degrees that was the half rotation, and that should give me what's left. So I'm going to take 225 degrees, subtract 180 degrees, and that gives me a 45-degree angle. So this reference angle is 45 degrees. And now that I have a reference angle, I can pick some point along this triangle and draw my reference triangle. And so now this right here is the triangle that we're going to use in order to calculate cosine of 225 degrees. So if I'm going to find cosine of 225, there's now a couple of ways to do this. So let's start with method 1 here. Even though it's basically the same thing, it's just two different ways to think about this process. Okay. So one way to do this is to say, I'm trying to find cosine of negative 225 degrees. So I should realize that that's actually going to be the same value as cosine of 45 degrees. Except it's going to be cosine of 45 degrees in quadrant 3. Or I'm sorry, in quadrant 2. Now I already know that because I'm in quadrant 2 and I'm taking cosine, I know that my value will be negative. So that just simply means that my answer is going to be negative of whatever cosine 45 degrees is. So now we can go back to our triangle and fill in the blanks. So we've got that this is 1 and this is 1, and therefore the hypotenuse is root 2. But more specifically, let's be careful here. Since I'm going backwards into the second quadrant, this is going to be an x value of -1 and a y value of +1. So now we see that cosine of 45 is 1 over root 2, or adjacent over hypotenuse. And when we multiply by the radical of 2 on the bottom, it gives me the actual value of negative root 2 over 2. So that's one way to do it. Method 2 is actually not thinking about it in terms of cosine of 45 in quadrant 2, but just drawing the reference triangle here, and now realizing that cosine of negative 225 is represented by my ratio of x over r. So now that I have the sides drawn for my particular reference triangle, I just have to reference the fact that the x value is -1, the hypotenuse is root 2, which sure enough gives me the same value of negative root 2 over 2. It's just two different ways to think of the same process, but at the end of the day, what we're trying to do is find the trigonometric function values of these particular angles.